Good morning, FOR 345. Welcome and a happy Veterans Day to you. I'm here in the ESF TV studio live, but when you hear this, I will be actually in San Antonio at the Soil Science Society of America meeting. And so you have the luxury of, because of this studio, we get to record the lecture and produce it so that it's like I never left. And so we finish up with colloids. This kind of pulls together everything we've talked about in the last couple days and also brings us into lab this week. So a reminder, our lab this week is in 102 Walters. Don't forget to bring your textbook, bring your notes, bring your calculator, all the things you'll need. And of course, and you'll remember the exam is Wednesday, just a couple days away, 9:25 a.m., a 1-hour exam. And of course, no calculators, no phones. As my Ukrainian mentor would say, no anything allowed, just your pencils and paper. It's a 1-hour exam. I've cleaved it down to 6 pages. It was really long, and I've cut and cut and cut, so it's quite doable in the hour. And hopefully you've prepared for it. Maybe you attended the review session on Friday, hopefully. So previously on forest soils, last time we talked about crystal and clay structure and the properties of clays. Then we snuck in or put in particularly a big picture item. Then the idea that the soil physical and chemical properties are a function of the amount and type of colloid. And this kind of gets us toward the final exam where we look at 10, 11 big pictures and connect everything from the beginning of the course to the end of the course. And this is one of those I said, put a star by because you want to visit this and make sure you have it down by the end of the semester. We were talking about colloids and CEC. And CEC is interesting. I think I'm missing something there. CEC is pretty interesting because it's all operational. So we've defined it as the sum of exchangeable cations a soil can absorb. And so how do we determine that? And so first we leach out the salts, the soluble salts, and then we're ready to look at what the colloid has in the exchange complex. So once we have the soluble salts out, we'll saturate the exchange sites with a cation we know. In this example shows, of course, ammonium, NH4+. It's a cation, it's commonly used, and to do this procedure, and we drip this through, it's usually about 1 normal, it's very strong, and it's going to push everything off. So is all these other cations on the soil, calcium +2, magnesium +2, potassium, and so forth. These are all adsorbed cations, no salts, and now we're going to push these off, and we're going to replace these spaces, these colloidal spaces, with ammonium plus. Pretty cool, right? We've got a porous filter paper. We just drip this through, and voila. Eventually, we have pushed all those adsorbed cations down into the solution collection in this beaker, and we've replaced them 1-to-1 with ammonium. So wherever there was a cation adsorbed, now there was a ammonium 4 plus in its place. So now we've identified every one of those sites by occupying them with an NH+4 ion. Pretty cool, nice cation, and everything else is in solution, along with a whole bunch of other stuff. Now we have this beautiful soil. It's all saturated, and every site where we had a cation now is occupied by an NH4+. Okay? And so the next thing to do is, it would be nice if we could determine how much NH4+ we had. So how do we do that? So now we want to push these off so we can measure the amount of material we put on. To do that, we'll use another cation. This is potassium with some salt. And again, 1 normal solution that's going to push these ammoniums off and to replace them. So the only thing on this right now, on these colloids, this NH4+ is occupying all these spaces. We put it there to replace the material, the cations that we've displaced that are now down in the beaker. So let's displace what we just put on, an H4+. Let's pour this through, bloop, 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 bloop. And now all those potassiums, for each site where we had an NH4+, now we have a K+, it replaced it. All those NH4 are now in the beaker, along with this other stuff. But holy moly, look at this. Now the amount of NH4 here is exactly comparable to the amount that was in here adsorbed. All the adsorbed are now here in the bucket. All we need to do is figure out how much NH4 plus we have, because all the NH4 plus was up here in the adsorbed soil. Pretty neat, right? So that's relatively simple chemically. We can just do a titration, we can put this through the autoanalyzer, but we can determine the concentration that we have now of NH4 plus that we know came from these sites. We can determine the adsorbed cations, the amount of charge. Measure the NH4 plus. Pretty cool. Now we think about, let's take this idea one step further. We think about some cations as we like to keep track of, and we talk about this concept of cation saturation. Cation saturation. The idea is, let's compute what percentage of the CEC is satisfied by a specific cation. Why do we want to do that? Well, some of these are rather important to us, sometimes calcium, sometimes potassium, and we're interested in the amount of material that's taken up by those particular cations. So let's have an example. Let's compute percentage saturation, the proportion of CEC satisfied by a specific cation. Okay? And so here's my example. I'm giving you a CEC, and I have lab data that says the CEC for this sample is 10 centimoles of charge per kilogram, 10 cmol charge per kilogram. I've measured the calcium, 4 centimoles of charge per kilogram. Okay? So I have the total CEC, and I have the CEC that's taken up by calcium. Now we have what we need. Let's think about what is calcium saturation. That is, what proportion of this CEC, 10 centimoles of charge per kilogram, what proportion of that is taken up by calcium? Okay, so how do we do that calculation? It's pretty simple. The proportion of calcium as a function of total CEC. Okay. Oops. Got to go back one. Sorry about that. The answer to this question is 4 centimoles of charge per kilogram, that's the calcium, divided by CEC, 10 centimoles of charge. So 4 over 10 is 0.4. Right? So 0.4 is the ratio, the saturation of calcium to total CEC. What's 0.4 in percent? 0.4, multiply that times 100, so that's 40%. 40%. Let's see if I can write that. I'm going to try and make an annotation here. Let's use my pen. So we have 4 centimoles of charge, calcium, divided by CEC, 10 centimoles of charge, okay? And we multiply that times 100 to convert to percent. 100. Okay, so 4 over 10 times 100 equals, well, that's pretty easy. Cancel these zeros out. 4 times 10, 40%. 40%. How about that? All right? So the calcium saturation for this particular sample, 4 over 10 times 100, 40%. So what do we kind of review and think about this thing of CEC that we're measuring? It's operationally determined, so I can't stress this enough. CEC, I don't know if Briggs can't type anymore. CEC is operationally determined. That is, the method is kind of important, right? So we're using a certain set of methods to define this measurement of cation exchange capacity. There's a couple ways to do that, a couple groups, okay? And we're going to kind of compare 2 of those, buffered and unbuffered. So let's think about CEC, and generally we think about the buffered methods, and I'll explain, and we associate that with cation exchange capacity. Buffered methods. Now, we buffer, we force this pH at a certain value, okay, to make this happen. And so hence the buffer. We'll buffer this, and so we'll force this reaction at pH 7 or pH 4. We will control the pH, we'll control the pH under which this happens. And that's the idea of buffered. Now, in the soil, the pH varies, right? And normally pH isn't 7. Particularly here in the Northeast, we have a lot of acids and rains and a lot of weathering. The pH is often acidic. Okay? And so we know earlier, we talked about pH-dependent charge. We know that pH affects the number we get. So one way to get around that is to always do this at the same pH so we can compare across all soil types. And that's hence this idea of buffered methods. Okay? Pretty cool. And then we think, well, what about unbuffered? Well, what if we want a more realistic picture in situ of the CEC? We'd actually want to do this reaction, do this exchange at the native pH. If the pH was acid, we'd want to not change that. If the pH was basic, we'd not want to change that. Okay? We don't want to level it out and control and compare against all pHs. And so that gives us this idea, brings us to this idea of effective CEC. So we abbreviate that ECEC, effective CEC, E for effective. Okay? The idea is we are doing this reaction at the in situ pH, the pH that actually occurs in the soil where this soil is sitting. We're not going to do it at pH 7 because the pH of that soil is probably not 7. Okay? So we're talking about effective pH, effectively, effective CEC. Effectively, what is the CEC for that soil under those conditions? Okay? And we're going to use unbuffered methods. We're not going to mess around with the pH. If we use buffered methods, okay, we no longer think about effective. We just think about CEC. Okay? And that's the basic idea between effective CEC, what's actually occurring in situ, and this CEC by forcing a pH change, forcing it at some pH. Pretty neat. So what? Why does it matter? Well, it matters because pH affects charge. And a while ago, I've introduced the idea of pH-dependent charge. Here it is now again. And so we have this graph showing effective CEC, and you're familiar with the units, centimoles of charge per kilogram, right? And so we've used an unbuffered salt. We've actually done this exchange. We force this exchange at whatever the pH of the soil is, at native pH. And so we plot effective CEC, centimole of charge per kilogram, by soil pH. Soil pH here on the x-axis. And this goes from pH of 4, acidic, all right, and to pH 8.5, alkaline. And there's pH 7, neutral in the middle. Okay. And so what's this graph telling us? So this graph tells us that, for instance, I have here organic material, okay? And at pH 7, what's the CEC? So I do this at pH 7. I force this. I use a buffered method. Okay, so here I am at pH 7. To find my cursor, it's hard to find in this color. At pH 7. Okay, I go up, I look at pH 7, I do this, and I get an answer of 200 centimoles of charge per kilogram. This is the CEC of humus, the average CEC of humus. So that's at pH 7. Now, if I do this and I don't control the pH, I just do this at the pH of that particular soil, and that particular soil happens to be around 4.1, okay, and I measure that, and I measure this CEC. It's a lot less, right? It's about 100 and some centimoles of charge per kilogram. And this is just due to pH, right? The same soil, but here I've done it at the native pH, an unbuffered method, right? And here I've pushed the pH to 7 in my lab so I could compare across soils. And so when I do that at 7, I get an answer of 200 centimoles of charge per kilogram. When I do this around 4, native pH, which is a little around 4, it's about half that. Okay? So this is the nature of pH-dependent charge. Okay? And this is a particular example. And so this curve here kind of illustrates that. This shows, this curve plots pH, effective CEC by pH, and it increases. Right? So as pH increases, the CEC increases. It's pH-dependent charge. That's why it's important. That's why methods are important. Right? So now it makes a difference whether we use a buffered or an unbuffered method. If I am more interested in looking at the reality of what's happening in the field at a particular site, I use an unbuffered method. Ammonium chloride is a typical unbuffered method. If I'm interested in comparing a whole bunch of soils across the nation, across different pHs, I'll use a buffered method. Okay, I won't have effective CEC, but this allows me to control for pH and make some kind of comparison for a wide range of soils across a wide range of conditions. So unbuffered, no, I don't control the pH. Buffered, I control the pH. So it matters, and it matters because pH is dependent on charge. Sorry, CEC is dependent on pH. Okay. Then we can think about colloids, and so which colloids make the greatest contribution to cation exchange capacity? Which ones are really the movers and shakers doing the bulk of the work? Well, you'd have to think about that. You'd have to think about organic matter, okay, and texture. And so remember, the big picture item, that soil physical and chemical properties are a function of the amount and type of colloid. And so we can think about the CEC values across those different types of colloids. And clearly we're going to come out with a conclusion that the organic colloids have the highest contribution to CEC. Pound per pound or gram per gram, there's a lot more CEC for a gram of organic matter than there is for a gram of sand. Okay. So amount, let's look at first the amount. Last week, we looked at the amount and type of texture in a picture. I showed you a slide with 10% montmorillonite and 64% montmorillonite, and we visually saw the difference in cracks between that amount. And then I showed you the same kind of comparison for kaolinite, a 1-to-1 non-expanding clay. So there was a visual of this importance of the amount and type of clay. Okay. So let's take that a little further and put some numbers to it, right? Let's think about the humid temperate region, kind of where we are. And a rule of thumb in the humid temperate region here in the Northeast, each 1% of clay contributes about 0.3 of a centimole of charge per kilogram of CEC. So for every 1% clay increase, the CEC goes up by about 0.3. Okay? And that's a rule of thumb. In lab, you'll explore this a little bit, and we'll kind of work the numbers on this. Okay? But here's the rule of thumb. So what are the types of clays that are common in the Northeast in these humid environments? Fine-grained mica, chlorite, okay? Probably one of the more common types of clays. And let's see, we had a table, we had a graph, a table, a spreadsheet, and I kind of looked at the different colloid types, the silicate clays, and one of the things I asked you to remember was the average CEC. So if we think back to that graph, they think back to that spreadsheet, and we think back to fine-grained mica and chlorite, the average CEC was 30 centimoles of charge per kilogram. Okay? 30 centimoles per charge per kilogram. So every percent, we take a percent of 100 of that, so we work that backwards, this counts for about 0.3 of a centimole of charge per kilogram, based on the idea that the average was 30. Humids, we'll take the subtropics. Let's take the highly weathered places and think about what are the clay types there. Kaolinite, hydrous oxides, highly weathered, the silica's kind of leaving the system. Humid subtropics. Now we're looking at type of clay. And so let's look at this rule of thumb. Each 1% of clay in those systems contributes about 0.8 to 0.4 centimoles of charge per kilogram. So these numbers should kind of look familiar to you, right? And again, we think back to that nice spreadsheet that Excel spreadsheet that I had on the slide, and think back of what was the average CEC for kaolinite, and what was the average CEC for the hydrous oxides. And so we remember that the average CEC for kaolinite was 8 centimoles of charge per kilogram. Okay? And we remember that the average CEC for the hydrous oxides was about 4 centimoles of charge per kilogram, those highly weathered pieces. So again, if we think about that in percent, 100th of that, that's where this number comes from. Each 1% of clay contributes about 0.08 to 0.04 centimoles of charge per kilogram, depending on whether you have kaolinite or hydrous oxides. Okay? So this connects pretty nicely with the previous idea. That's one of the reasons that I've asked you to memorize that CEC values of the different colloids. We started out with the hydrous oxides, we went over to kaolinite, we looked at fine-grained micas, we did vermiculite, we looked at smectite, we went all the way up to chlorite and the organic matter in colloids. So that chart is pretty important. So there's a reason behind knowing those values, because we can kind of a rough idea of what the contributions are and what the CEC might be. Okay? So that's the reason I've asked you to memorize that. Besides, I can ask it on the next exam. There's a madness to my method. So we have now these reactions, we have these equations, we've got a pretty good foundation to think about. And one thing we'll do this week in lab, we'll actually balance CEC reactions in a very, let's say, a very perfunctory, not down to the 10th of a millionth of a charge, but we'll, in a perfunctory way, we'll balance these equations. So let's look at one for an example. So here we have a reaction. So here this depicts a colloid, right? Depicts a crystalline colloid with adsorbed calcium, potassium, and so if we're going to exchange with some NaCl, we're going to use this reaction. Here's NH4Cl. This is the salt we're going to use to force this reaction and do this exchange. And we're going to drip that through the system, and we might ask, how many NH4 pluses are needed to balance this? Okay. So the first question we look at, how many plus charges are needed to balance the adsorbed cations? Okay. And so this is pretty easy. Now we're going to connect what we did before in class. So I've asked you to know that calcium is +2, right? Because we know that now, because we had to memorize it. I've asked you to know that potassium is +1, the balance, right? And so here this counts for 2 charges, this potassium accounts for 1, this calcium another 2, right? This potassium another 1. These are balancing the negative surface, the negative charge expressed on the surface of this colloid in this particular example. So here we have 2, and 1 is 3, and 2 are 5, 1 are 6. And so we have to conclude that the first thing that we ask is, what is the charge on this colloid? And so now we add those up. So now we have -6. Okay? So if we have -6 here, we want to balance that with ammonium. Okay? What is the charge on NH4? It's +1. I've asked you to know that, right? So if I have 6 here, negative charges, and I have 6 positive charges, I need 6 of these NH4 pluses to balance this. And so I fill in, the first thing I fill in is this magic number here, 6, because I have looked back and decided how many charges are accounted for by the cations on this picture. 6, 1-to-1, 1-to-1 replacement. So now if we run this reaction, right, I'm adding ammonium chloride, NH4Cl. What goes on to the exchange sites? Okay, so I'm pushing this reactions. Well, you'd have to say it's ammonium, right? NH4 plus is going to be replacing. Okay, so let's see, you have calcium +2, NH4 is +1. I need 2 of these, right? So if I'm going to take care of this spot here, I got to throw 2 NH4 pluses there. There's one of them. Okay, that takes care of one of the calciums. But calcium +2, I got +1, so I need another one. Bam. Now I've taken care of this spot here. What about potassium? Potassium's +1. So I need one NH4+, because that's +1. Okay, that takes care of potassium. I got to go down to the bottom part of this. I got another calcium here. I must need two NH4+, right? NH4 is +1, so let's put them down here. Let's replace the calcium with that. There's one of them. There's two of them. Now, the only thing left, I got to take care of this potassium. That's a +1, so I need one of these to replace it. There. Now I've balanced the charges. I've counteracted where I pushed these things off with enough charge of ammonium to replace it evenly. Okay? And so what's out here in solution? What have I done? Well, the calcium has come off and the potassium's come off. Right? So I have calcium and I have potassium. Okay. How many? I've gotten two calciums and two potassiums. There's two calciums there and two potassiums. Getting warm. Now, what is the anion balancing these? I have chloride, right? This is ammonium chloride. Chloride's still there. Okay? So calcium is +2. Right? So it has to come along with two chlorides. Right? And potassium's +1. It's got to come along with a single chloride, so KCl. Right? So let's see. It looks like I need 6 ammoniums. Do I have 6? 1, 2, 3, 4, 5, 6. Okay, that's going to be right. Now I have ammonium, 6 of those. Chlorides, okay, I need 6 of those. Right? So I look down here, I've got 2 times 2, here's 4 associated with this one. There's 2 for CaCl2, there's 4 of them. Here's 2 KCl's, KCl1. So 1, 2, 3, 4, 5, 6. Right? Pretty cool. So now I have this balances out. So there we are. I've now balanced this equation. I first balanced the charge. Right? I then replace with the appropriate number of cations, and then I make sure that the cations coming off are balanced out here. So let's see, there's 2 calciums, yep. There's 4, 6 chlorides, yep, there's 2 potassiums. So this is now balanced. So that's the way to balance the reaction. So thinking back, we started with the charge. We moved from the charge to figuring out what got pushed out, what went on, and then we had to go into solution and balance the anions associated with this salt with the cations that came off. And that's all there is to it. Okay? Pretty slick. Now you'll do this in lab a little bit this week, one of the things you'll do so you get some practice. But all coming forward. And so I kind of wrap that up with this slide. Okay, so this slide summarizes what I've just drawn with my 6-year-old crayon hand. Right? And here's a clean slide in showing what we did. Right? We had the 6 charges, -6. We balanced that with 6 ammoniums. We have 6, it took 6 ammonium chlorides. 2 of those were calcium chlorides. 2 of those were KCl. Pretty slick. You can do this, and you will do it this week. So let's leave us with some homework, right? Leave you with some homework to get a little practice. So here I'm going to give you a little exchange reaction. And we have here 2 calciums, 3 calciums, 4 calciums, right? And a couple potassiums. And we're going to displace that with sodium chloride. Right? So your job is to finish this reaction at home. We'll look at it next week and tell me what this end looks like. Okay? And tell me how many of these NaCl's it takes to do this. And then tell me what's in these positions and how many. Right? So we're going to have calcium, potassium. So you'll answer this piece and this piece. You can balance it. That'll be it. So we've talked about positive charges, and now, or it's not positive CEC, now we got to talk about the other way. Right? So sometimes soils, colloids can exhibit a net positive charge. Kind of thing, weird. We've been really focusing on net negative charge, right? But let's consider the conditions that generate positive charge. How and why? So the thing is, we talked about pH-dependent CEC, and so now we'll look at the extremes. High acidity, low pH, we can get a positive charge. Okay, so high acidity, low pH. Here in some colloids, it's quite possible and common to have a net positive charge. Pretty wild. So let's just think about the mechanism for that, first of all. So there's a lot of hydrogen around in low pH. And when there's a lot of it around on some of these broken edges, these hydroxyls, it will tend to be attracted to the OH's end of these and actually electrostatically bound, and so we'll actually have a positive charge because we have OH and we put an H plus on that, bounds, it joins to this oxygen, and we get a positive charge. High acidity, a lot of this stuff around in solution. And it looks like this after we take care of that and get those broken edges. Now we have a net positive charge. Again, high acidity, low pH, okay? pH-dependent CEC. So this leads us up to another exchange. Anions can exchange. Right? So we've been focused totally on cations. But if we kind of think about this system at a very acidic pH, now we have the opportunity to think about the exchange of anions because of a net positive charge. So here's an illustration of that in this slide. And we'll talk about anion exchange. Right? We've talked about cation exchange. Now we'll talk about anion exchange, the exchange of negative adsorbed ions of these net positive charge for one in solution. So here's, again, pointing out net positive charge, okay? Net positive charge. Low pH, high acidity. And here we have nitrate, okay. It's attracted. It's an anion, right? This is an anion, but because of this low pH, it's attracted to this net positive charge. We can displace that anion, nitrate, a very common one in soils, which we'll review in the last couple of weeks, with chloride. So instead of a cation exchange, we have an anion exchange. We're going to exchange this chloride in solution for the adsorbed or attracted nitrate on the colloid. Anion exchange. Change places. What kind of colloids? So I did spend some time thinking about colloid types, and another reason to think about colloid types, there are some that are prone to anion, to this net positive charge under low pH conditions. And these are some of the iron aluminum oxides, gibbsite, goethite, also some of the non-silicate clays, allophane and ammogalite. We talked about all these types. And another nice thing to know about these types is that can have a net positive charge under high acidity, low pH. Pretty wild. We'll reinforce this next week when we talk about soil pH. We'll keep the connection going. But now we'll just take it on fact that there's possible to have a net positive charge. And these colloids, gibbsite, goethite, the iron aluminum oxides, right, that we've talked about, And then the non-silicate, or the non-structural silicate clays, non-crystalline, allophane and amogolite. Okay. These, under low pH, high acidity, can actually take on a net positive charge. So now we think about exchanging anions instead of cations. Right? We have adsorbed anions for these particular. It's kind of really neat for allophane and amogolite because these two really glom onto phosphate, okay, an anion. And so here's the illustration. It's the same as with cation exchange of a balanced reaction, a net positive charge. We replace the nitrate with a chloride. Okay, make this exchange. And it looks like this. Now we have the chloride, this net, associated with this net negative charge. And now in solution we have the nitrate. So we've exchanged and adsorbed or attracted nitrate on this low pH system, this colloid, and exchanged that with a chloride. Anion exchange. Not anion, but anion as negatively charged, as opposed to a negative ion. Pretty wild, right? Most systems aren't really all that acid. So the dominant thing we talk about is cation exchange and this attraction for positively charged ions to negative surfaces. But we do have conditions, as we've just seen, where we have a net positive charge. Again, high acidity, low pH. This is an interesting, just a reality. Pretty neat. So now we consider how strong are these cations. We go back to cation exchange. How strong, how tightly are they attracted? And so there's a sequence of attraction. And it depends, the strength of attraction, how tightly these individual cations are held, all other things being equal, depends on two things. Okay? The valence and the hydrated radius. Okay? So we know what valence is, right? +1, +2, +3. But I haven't told you about hydrated radius. Not particularly. So when a cation travels in solution, okay, it's because water is a polar substance. Cations have a shell of water, right? There's a shell of water. Each cation kind of moves around with a shell of water attracted to it. And so this attraction is much stronger and much tighter for the higher valences. So potassium and sodium +1. Sodium in particular, kind of bulky, right? So it's moving around, but it's only a +1 and just trying to fit around these. If I take this colloid and put it in solution, and this colloid attracts cations towards it, and just put it, I'm going to mix some up. You'll do this week. You'll mix up, we have mixed up some bentonite, which is a 2-to-1 expanding clay. We bring that in lab, we've mixed that up and put it in a solution, a 1% solution. And you're going to add some things to it. You're going to add aluminum to it. You're going to add calcium to it and see what that does. Okay? And so we come back to what's happening has to do with how strongly individual cations are attracted to colloid surfaces. And it depends on these two things, the valence and the hydrated radius. Okay? So let's start out with this series. Here's aluminum +3, the very strongly attracted, right? It's a +3. It has a very high valence. Okay? And when aluminum floats around in solution, it's really pulling in those water tightly to it. Right? So it's a nice, tight, hydrated radius, a small hydrated radius. Next one down is calcium +2, a little less stronger, a little less valence. Okay? It's still pretty tight, but not quite as tight as aluminum. So here you have calcium, a calcium ion floating around. It's kind of got a little bigger hydrated radius, but it's still pretty tight. It's a little bigger than magnesium, okay? A little tighter. And then we get to K+, ammonium, about the same attraction. And then we get down here to the other end, Na+. This is probably the most weakly attracted. Okay? And sodium, it floats around, and it's just a +1, has a very large hydrated radius. So you picture sodium in solution, a sodium ion floating in solution, and it's rather large, bulky, with a bunch of water around it, H2O, oriented to the negative side of that. And so it's this large, think about a shell, a large shell of sodium. And then we go over and put aluminum in there. It's very tight. It holds that in very tightly. And so we're traveling around with a small shell. And so how do we overcome it? Mass action. Okay? So all other things being equal, aluminum is going to be held more tightly than calcium, the magnesium, and so forth. This is very weakly held. This is very tightly held. So we're doing these CEC reactions, right? But when we do a CEC reaction, we're pouring in material, usually 1 molar, really high concentration relative to the soil solution. Soil solution, we look at these, they're millimolar, 0.01, 0.02, kind of low concentrations. Now, if I take something like ammonium, okay, NH4 plus chloride of salt, and if I was just looking at small concentrations, it would be hard, it would be difficult for me to displace aluminum with that. It would be impossible. So how do I overcome that? I just blast it. I use mass action. I just pour concentrated ammonium chloride in there, 1 normal, in a system where I have millimolars, very small normality, low normality. So it doesn't matter that it's more strongly held. I just overwhelm the system by the amount, high concentration. That's why I use usually 1 normal. We use pretty high concentrations to do these leaching experiments. We want to push everything off, regardless of whether they tend to be held more tightly or more strongly. And so we call this mass action. So we overcome this attraction, this relative attraction for cations strength by mass action. We'll demonstrate that this week in lab, and we'll actually demonstrate this attraction as we look at what happens to clay in suspension when we add something with a very tight hydrated radius, like aluminum, or when we add something that's very bulky. So you'll get to see that play out in lab this week. Think back to this slide. Here's a picture of that, a nice illustration from the book that I've kind of talked about it with my hands, and let's talk about it with a picture. So here's an example of a root. We've got a root exuding hydrogen ions. Okay, pretty cool. And then we've got a micelle. So what's a micelle? Remember, a micelle is a clay, okay? So a clay crystal. So here's this root, okay? So it's pumping out hydrogen. There's all kinds of things going on. One of the things it pumps out is hydrogen, okay? Acidity pushes it out. That hydrogen, all the things being equal, would like to replace sodium. Sodium is pretty bulky, okay? Could happen. Sodium very loosely held. So what happens if something's tightly held? Well, something like aluminum, very tightly held. Now you can imagine what happens around that micelle. It attracts, but you can fit in, because of this hydrated radius, showing the shell, you can fit in a lot more of these aluminum ions, +3. They're small, packed, high charge density, okay, compared to sodium. So where I had this sodium, now I can fit in a whole bunch of aluminums, and I can actually counteract this attraction. Okay? So I can physically effectively counteract the negative charge in this micelle. You'll do it this week in lab. If you counteract the micelle charge, they don't repel. And then when they don't repel, they can come together, and van der Waals forces hold them together in solution. They'll actually clump, they'll flocculate. This is a real nice illustration of that. So that leads me to something you'll observe in lab this week, flocculation, the clumping, aggregation, clumping of micelles in solution. We have bentonite, a clay, 1% solution. We've mixed them up, it's colloidal. All these bentonite are in solution. How can I get them out of solution? I could get them out if I could cause them to clump, okay? They're not going to clump just by themselves because they're net negatively charged. But if I can overcome that net negative charge by putting something in there that will overcome that, I can make them clump or flocculate. You're going to do that this week. Pretty awesome. You're just going to do so much in lab this week, it'll blow your mind. Well, so to clump or not to clump, that is the question. And part of the lab is thinking about why you're observing what you do, what you see. And here's the story. right? So let's start out with the story. Net negative charges repel. Okay, so that's a story that we've been harping on. Net negative charges, they repel. Why is that important? So my cells, we mix these up in solution, they have a net negative charge. They tend to not want to clump. They stay away from each other, right? They're like negative ends of a magnet. They repel each other. And they stay in solution. It's colloidal. Okay? They're too light to settle out by gravity. So how can I get them to clump? How can I get them together? I need to neutralize the net negative charge. If I could take that net negative charge out of the picture, when these things come together, they're so small, the forces, van der Waals forces, would hold them together. I can get them to flocculate. How do I do that? Well, I can counter that by adding a cation that has a very small hydrated radius. What would that be? Well, we just looked at a bunch. What was the one that's more strongly held, has the highest valence and the lowest hydrated radius, the smallest hydrated radius? I remember that's aluminum, right? So if I can add aluminum to the system, I can counteract that charge and I can actually force them to clump, almost to the point it looks like jelly. So you'll see that this week. Suppose I try this and I add something like sodium with a very large hydrated radius and a low valence. I just can't get enough of those sodiums with their hydrated radius. I can't get enough of them around my cell to neutralize the net negative charge. Can't do it. So they're going to stay in suspension. They're stay in solution. So I could add sodium all day and I'm not going to do anything. But boy, put a little bit of aluminum in there, flocculation. Pretty wild. So pay attention to that. That's one of the experiments you'll do this week. How can I summarize that idea of valence and hydrated radius? So I put those two together in the same idea and talk about charge density. Right? Charge density, a high density of charge, small hydrated radius, large valence, a high density of charge. That's the material that I want to add if I want to have flocculation. So let's put this on a graph and think about flocculating agents and dispersing agents. Let's take this one step further. And secret agents. And you'll recognize a mad caricature of James Bond, not the original Sean Connery, but one of the more recent Bonds. And flocculating agents have a high charge density. Right? They have a high valence, which leads to a low, small hydrated radius. It flocculates. It will counteract the net negative charge in my cells, clays, and suspension. And it's the same series we just looked at. Aluminum +3 has a higher charge density than calcium +2. Okay, and both of these will flocculate. And by the time we get down to ammonium, by the time we get down to sodium +1, it's dispersing. Okay, it's just unwieldy. Let's say a big, bulky, hydrated radius and a little amount of charge +1. And so it's dispersing. You can't get enough of those around in my cell to overcome the net negative charge. And that's how it works. And so, again, we overcome this. Sometimes we want to push everything off, even if we use only something like sodium chloride or ammonium chloride. But we overcome that. We just use a high concentration, mass action. So I'll use a 1 normal. The typical solution to do this for effective CEC is 1 normal ammonium chloride. And this was a big deal. Back in the days when we were doing the acid rain research, most of the CEC was done at pH 7, right, from ag. Ag does a lot of things pH 7 is the sweet spot for most ag plants. That's where they have the best nutrient availability. And we'll talk about that later on. But we want to use ammonium chloride to get effective CEC. We can't, if this was a small concentration, we could never replace an aluminum +3 adsorbed with an ammonium. But if I just blast the system with 1 normal, a whole bunch, that's how I do it. That's mass action. I'm pushing everything off. Even though it's more strongly attracted on an ion basis, I'm pushing off aluminum and everything else. So pretty cool. And so we think about one normal, 1 molar, how many centimoles of charge? So that's one to think about as you ponder things tonight, being able to think about the centimoles of charge and a mole of charge. Should be a fairly easy answer for you by now. So that brings me to kind of think about pulling it all together. And so I wrote a little limerick, as I'm prone to do. There once was a cation called Na that hydrated in a large sort of way. Applied to fields made things worse, as the PEDs did disperse, but for texture it gets the okay. So think back to the physical properties lab and texture, and think back, what was that dispersant that we used to make sure that our clays stayed in suspension and didn't flocculate, because we needed to have those clays in suspension because they affected the density of water. We wanted to measure the texture. So that was important. Pretty wild. And let's think about the other end of that, right? Let's think about, there once was a cation called Al, aluminium. For flocculation, it seemed to excel. Put in bentonite suspension, you'll remember that clay, permitted no retention. As the aggregates to the bottom, so fell. And think about the gentian violet you'll see this week. Pretty cool. And the last piece to put this all together, Genesis. Not the band, the great Phil Collins, but Genesis, and not the beginning of the world, but the genesis, how silicate clays are made. How are those clays made? Well, we can think about their relationship with weathering in landscapes. So a couple of ways. So clays come, silicate clays, they come from primary minerals. So remember, we talked about parent material, and we talked about aluminosilicates, those primary minerals that generated clay. Things like hornblende and things like feldspars and things that didn't generate clay because they were secondary minerals. So we can take those primary minerals and alter them, just move things around, make them a little smaller. Or we can take those primary minerals and just blast them apart with weathering, breakdown, recrystallization, intense weathering. So both of those are pathways to clay. One's very intense, high energy systems, one a little less intense, just simple alteration. Not simple, but less intensive, less intrusive alteration. And so with that idea, we kind of introduce this idea of a weathering sequence that relates to the genesis of silicate clays. This picture in the text, this figure, 8.33, kind of says it all. So here we're going from mild weathering, increase in weathering rate, we're going from mild to strong, right? Very intense weathering, very mild weathering, increasing weathering. So as we increase the weathering rate, the CEC goes down, cation exchange capacity goes down. The anion exchange capacity goes up. We get to these high weathered systems. So this is showing the charges on clay colloids, okay? And we've got plus, right, and minus. So here we actually have anions being adsorbed, and here we have cations being absorbed. So we start out in mostly 2-to-1 clays. They're slightly altered. They tend to be relatively high CEC. As we get more and more to the 1-to-1 clays, the CEC goes down. And as we get into the highly weathered iron aluminum oxides, the CEC goes down further and actually gets a propensity for anion absorption. So this sequence is pretty useful to think about. This is trying to depict some of those red, highly weathered systems of hydroxides. This is now trying to picture some of those 2-to-1 expanding clays. Okay? And here it is in showing the impact on CEC associated with weathering. Increased weathering intensity, reduction in CEC, CEC is going down, and increase in anion exchange capacity down here. Pretty cool, right? and think about the weathering of that. Let's look at that in more of a diagram with primary and secondary minerals. Let's go back to the diagram we started out before with primary and secondary minerals. And here we have the range. Here's microcline, orthoclase. These are feldspars, high in potassium. Here's muscovite, right? And then we have the micas, biotite, the iron, and mica, and then with primary chlorite, so primary minerals. So we can alter those, right? So take muscovite, remove some of the K, get fine-grained micas, okay? Remove some of the K from those fine-grained micas, get the vermiculite. Chlorite, remove some of those and get the vermiculite. Okay. Those continue to weather. Those vermiculites can weather to smectite as we remove more and more magnesium. Okay. And the smectite can weather to kaolinite as we remove silica. So progressive weathering, alteration, removing of silica. Or you can have this very intense weathering, hot, wet climates, and get recrystallization, right? So recrystallization, and go directly to oxides of iron and aluminum. So more intense weathering, more toward the 1-to-1 clays, and then more toward the iron and aluminum oxides. And this is a nice picture of it. So at the beginning of the sequence, primary mineral composition is pretty important. But as you get later and later in the sequence, weathering becomes less important, less dependent on the primary minerals and much more dependent on the intensity of weathering. So that wraps up colloids, right? And I've got a prelude to acidity. And to think about the next thing we'll talk about, pH, acidity. So here's a little diagram for you to ponder as you leave and think about colloids and get ready for the exam, which won't cover colloids, but you'll be in lab this week. pH, little p, H. What does that stand for? Here's a picture of what pH stands for. Okay, P. Okay. So I'm going to close with that and ask you, what is little p, and how does that relate to this picture? And next week, we will hit acidity. So good luck on the exam Wednesday. I will see you when I return from San Antonio. I hope that you've made the review session, which I'm going to have in about 5 hours. So long for now. I'll see you next time.